Good morning, everybody. Welcome to the morning session. My name is Konstantin Khanin. I'm working here in Bimsa, not for long, but I'm local. We have 3 talks today by Professor Pierre Colmez from Sorbonne University. He is actually CNRS Director de Research. And Pierre is a winner of several awards. He was a speaker at ICM in 98. And he got 2005 Fermat Prize for his work on L functions and Galois representations. He also won 4 times the championship in Go in France. And today he will speak about Hodge theory for periodic varieties.
Okay.
So Pierre doesn't mind if you ask questions during his talk, but please don't overdo it, okay? Thank you.
Okay, so thanks for the introduction. I will try not to go over time by 15 minutes like last year. So I will speak about Hodge theory of periodic varieties, but what my main interest is in analytic varieties. So let's start with some example. So all of I'm going to say is some joint work with Wiesława Nizio. And this is a word in Polish. And partly with Gabriel Dospinescu and Sally Gilles. So example, we start with Y, the unit ball, open unit ball over C. So this is an analytic variety of dimension 1. So we have a lot of cohomology groups that you can attach to it. So you have the RAM cohomology, which is given by, it's one-dimensional if I equals 0, and it's 0 if I is bigger than 1. And you have the Betti cohomology with Q coefficients. You get Q if I equals 0, and you get 0 if I bigger than 1. And then you have the same thing, but with compact support. Then you find C if I equal 2, and 0 if I is not 2. And the same for Betti cohomology. I equal 2, and 0 for I not 2. And so just by inspection, you see that you have some isomorphism Hi the RAM of Y equals C tensor Hi Betti. And same for Hi with compact support. So, and you also have dualities. Hi the RAM to Hi the RAM with compact support, 2 minus I with compact support. That goes to H2 the RAM with compact support, which is C. And this is a perfect pairing. And the same with Betti. Okay, so everything works nicely. So now let's go to periodic world to see what we get. So we start from QP, and then we define CP to be the completion of the algebraic closure of QP. And we take Y to be the unit ball, open unit ball, over CP. So it's a one-dimensional analytic variety over CP. So for Hi the RAM and Hi the RAM C, which is also defined by using differential form, so you get the same answer, but you have to replace C by CP. And now what plays the role of Betti cohomology is the étale cohomology, in fact with QP coefficients. And in fact, it's better to do the pro-étale cohomology. So the difference between étale and pro-étale is that for étale, you do everything locally with ZP coefficients, and at the end you inverse P. And for pro et al., you do everything locally with QP coefficients. And so you get something much bigger. And so HI pro et al. Of Y with QP coefficient, then you find something which is quite different from the Betti homology. You find QP if I equals 0, so that's the same. You find 0 if I bigger than 2, but if I equal 1, you find the functions on Y modulo the constant. So if I equal 1. And if you compute, so this you can you can see by what I'm going to say later, which is a special case of what I'm going to say later. But this one you can also prove directly using Kummer theory to compute this cohomology. But now the pro et al. Cohomology with compact support, still with QP coefficients. So you find 0 if I is not 2. And you find some strange group, so it's the function on the boundary modulo the function on the entire space if I equal 2. So what is this boundary? So O of delta Y. So delta Y is what I call the ghost circle. The O of delta Y is defined to be the inductive limit of the functions on Y minus W. So W, where W is affinoid. So affinoid is the same thing as compact in this setting. So you remove all compact subsets of Y and you go to the limit. So at the end, you just get the boundary, what it is. So that's why I call the ghost circle, because you removed everything that was inside. Okay, so this has no point anymore, but still it has functions, and that's the statement that you get. Okay, so you notice several things. So first thing is that H1 et al. And H2 et al. With compact pro et al. Sorry. And pro et al. With compact support are huge. Really huge. The second thing is that, okay, I spoke of CP here. So if you are over the complex number, then there is this Gelfand-Maser theorem that tells you that there is only one version of complex numbers. But if you are over the p-adics, you have a lot of choice for the CP. So you can base change. So you have a lot of fields which are algebraically closed and complete for the p-adic topology, and which are not isomorphic to CP. So you could base change to any of them, and then the answer would be different, because the functions are going to get bigger if you extend the scalar to a bigger field. Okay, so and they change by scalar extension to a bigger CP. In quotation mark. So there are many possible CPs in p-adic. And the last thing is that it does not look very good to have a duality at first look. So if you want a duality like before, sorry, I forgot. And then there is a plus QP here, which I forgot. So there is a map to QP. So there is still a map to QP. But if you look, you would get, so this group here and this one here are actually in duality, because O of Y mod CP this is isomorphic to H0 of y of omega 1. If you have a function, you associate its differential. And so this is because the Durham cohomology of y vanishes. And the other group, O of dy mod O of y, this can be interpreted as H1 with compact support of y with value in O. And so these two groups are actually in duality, in Serre duality. So they are in Serre duality, but as vector space over C, over CP, okay? But not over QP. So why? It's because CP is an infinite extension of QP, and so if you have a duality over CP, it does not extend to a duality over QP because CP is not its own dual. So, so that's one problem, and the other problem is that if you try to make, so it looks like these two things could be in duality, and this should be in duality. But also what is wrong is that the numbering does not add up. You would have a duality between H1 and H2. So numerology does not add up. Okay. So these are problems I want to address in my talk. So now let's start with a general situation. So K is a complete for the p-adic valuation, which we assume that it is discrete on K. And our C is going to be the completion of the algebraic closure of K. I start from y over K, so it's it's a smooth, geometrically connected so this is important, but this is not really important, just to prevent me to make stupid mistakes in my when I write a statement. So it's supposed to be analytic varieties, but with some other convergent structure. Which means that if you are over an affinoid, which is inside your variety, you are given yourself a way to decide that the function extends a little bit outside your affinoid. Okay. So there are many examples of these things. So, for example, a G, you could take proper varieties, or you can take Stein. So Stein means that you have an increasing, strictly increasing union of affinoids. You can take the analytification of any algebraic variety. Analytification of algebraic. What else? Some other convergent affinoid is okay too. Etc. I mean, basically anything is in this category. So the theorem that we prove, which we call the basic comparison theorem, is that we have a long exact sequence, so n is less, so we choose some r, and we take some integers which is less than n, and then we have a long exact sequence that expresses the pro-étal cohomology group that goes like this. So I will define this object just now. So the groups that you really want, pro et al, of YC, YC with the value in QP goes to, well, except that I put R, so let me explain later, R's Rn, dr Rn. So what is this? So this is the Tate twist. So because we are over some algebraically closed field, you don't see it, but it's important to remember it for psychological reasons. So I put it here. So it's the same group as pro et al of QP. So what are these? So X R I. So I have to define this also. It's HI Yodo-Kato of Y tensor B. So I have to. So I write them and then I explain what they are. And this dr Ri is the HI of some sheaf, which is the Durham complex of Y tensor B Durham plus mod phi R. So now let me tell you what these objects are. So first thing is that, so this ring BST plus that appeared is B plus Chris of log P, and B plus Chris, B Durham plus are the rings constructed by Fontaine. So Fontaine's p-adic period rings. So I don't want to give the construction because when I started doing mathematics, Fontaine was giving a lot of talks about his theory. And every time he was constructing these rings, and after 40 minutes, he had finally constructed the rings, and then he had no time to say anything. So I am not going to make the same mistake. But just let me tell you some of the features. So on this thing, you have an action of Frobenius and the monodromy, which is just the derivative with respect to this log P. And you also have an action of the absolute Galois group of GK. So you have n phi equals p phi n, and GK commutes with everything. And on this thing, you also have an action of GK, and you have a filtration, a decreasing filtration. Okay, and in particular, if you look at B Durham plus mod field 1, you just get your field C. And one important thing is what we call the fundamental exact sequence, is that you have this QP of R can be read inside this these rings in the following way. So it's the kernel of the map from the eigenvalue of Frobenius on B plus Chris to B Durham plus mod field R. So this is what we call the fundamental exact sequence of p-adic Hodge theory. So that's for the rings. Now what is this group here? So this group is what we call the Yodo-Kato homology. So that's Yodo-Kato. So it's a refinement of Durham homology in the following sense. So first of all, you have a natural isomorphism. When you extend the scalar, yeah, so I did not define this, I will. HI Durham. So this C and R is the maximal unramified extension that you can find over C, and so in practice, this is defined as the limit over all field inside the algebraic closure of the residue field of K of W of K 1 over P. So it's really the maximal unramified things you can find inside C. So on this Giotto-Kato cohomology, you have an action of phi, an action on n, and an action of gk, like on BST plus. So which explains that you can tensor and take the diagonal action is here to define this subspace. Okay, so part of the theorem here is actually the construction of this Yodo cohomology. So the construction that we give is parallel. So is parallel. It was, I mean, we tried to copy what Bellinson was doing to Bellinson's. And so Yodo-Kato treated the case where when YK has a semi-stable model, and Bellinson removed this hypothesis by using the fact that, in fact, locally, for the étale topology, you always have a semi-stable model. That's the theory of alteration. So for algebraic geometry, this was done by De Jong, but in the setting of p-adic geometry, p-adic analytic geometry is due to Hartle and Temkin. Okay, and I should mention that there is an alternate definition by Binda, Gallauer, and Vezzani, which use using Ayoub's analytic motifs, so using Ayoub's so in the definition of Ayoub's motif, you also have the alteration of Hartle and Temkin. And so the philosophy is that this Yodo-Kato cohomology only depends on the special fiber. So it's something that's that you can compute using only the special fiber. And basically what Ayoub's does is to cut, to reduce any analytic varieties like this to their special fibers. That's what these analytic motifs do. Okay, and the Doram cohomology, on the other hand, here you have the Hodge filtration that really depends on the generic fiber, whereas this depends only on the special fiber. Okay, so reduction mod P or generic fiber. And so, and this HI, HK, so it's a projective limit of finite dimensional CNR vector space, CNR module. And on each of these finite dimensional things, the action of GK is smooth, so locally constant. Smooth action. So in particular, the inertia acts through a finite quotient on each of them, but not on the cohomology of the entire variety, because the entire variety can be big and the action can become more and more complicated when you reach the boundary. Okay, and so what you get from this is actually a relation between pro-étale cohomology and differential forms. Okay, so this theorem, in fact, is a combination of two theorems. What? That's the one. So it's hi of this complex. So in fact, this theorem is a combination of two theorems. So I mean, the proof starts from this fundamental exact sequence that I wrote. But now I'm going to put a double bar. So now you have a double bar, and so it means that we are looking at these rings, but as sheaves on the proetal side. So as sheaf of periods. And so the idea is to replace this QP, that is very simple, by these two objects that are much more complicated. But actually, the cohomology of this object is much easier to compute than the cohomology of this one. And so when you do that, what you get is the first theorem, is that you get an isomorphism when you truncate at R between the R gamma proetal of YC with value in QP of R with another complex that I'm going to tell you what it is. So it's a complex of symptomic cohomology, which is defined in the following way. So R gamma symptomic of YCR is by definition the mapping fiber of the following complex. So R gamma Chris of some model of Y, phi equal P to the R, goes to R gamma de RAM of Y C mod phi R. So here what is Y? So you don't have a semi-stable complex. As I told you, you have locally, for the Yetal topology, semi-stable models, okay? And so what you do is that you do hyper-coverings with everything having a semi-stable model, and then you compute with the crystalline cohomology of this thing. Okay, and that's the first theorem. And the second theorem is that now if you try to compute this complex, R gamma Chris of Y phi equal P to the R, well, then you get the complex computing Yodo-Kato cohomology. Yodo-Kato of YC tensor BST and n equals 0, phi equal P to the R. Okay, so that second part is more delicate than the first part, in fact. I will. Yes, I was supposed to give some examples, sorry. I will now. So as Javier asked, there are some examples. So the first one is when y is proper. Then in that case, this long exact sequence splits. And so you get short exact sequences like this. Hn pro et al. Goes to x Rn, goes to dr Rn, goes to 0. And now all the cohomology groups are finite dimensional. So all the spaces that are here are easy to understand. And Hi, Hk, Hi de Ram, and Hi pro et al. Finite dimensionals over their respective fields. So this is exactly like in the algebraic case. In the algebraic situation, you have exactly this exact sequence that allows you to give you a description of pro-étal cohomology in terms of de Ram data. Okay. The second thing, so I'm not going to give the ball, but I'm going to give the affine space, which is basically the same. So in the affine space, affine space of dimension d, then the de Ram cohomology is 0, and so the the Yodokato of cohomology is 0 if n is bigger than 1. And so what you get is an isomorphism Hn pro et al. Of yc with value in qp of r. So this is isomorphic to omega n minus 1 of yc modulo the kernel of the differential, and you still have a twist r minus n, which plays no role. So if you replace the pro-étal cohomology by the étal cohomology, in that case you would get 0. Which basically tells you that you don't have any differential forms on the entire plane which is bounded. That's what it says. If you have a global differential form, it cannot be bounded. So more generally, if you take something which is Stein, so which means that it is a strictly increasing union of affinoids, and it also means that the cohomology of any coherent shifts vanish in degree bigger than 0. Then what you get is an exact sequence. So this induces an exact sequence that has the same term on the left. Sorry, I'm taking n equal r now. Goes to h, so this is hr of yc qp of r. And then the term on the left is this xrr goes to 0. So as I say, this pro-étal cohomology of qp of r does not depend on r, but the way you compute it depends on r. But and so it's better to take r equal n if you want to do the computation in the Stein case. And is that so? Yeah. So you see, I mean, if you go from compare proper and Stein, you get very different answers. Right? And so we have something we call the CST conjecture. That interpolates between these two results. And so if you use these two theorems and the definition of this as a mapping cone, then you get the long exact sequence of the theorem. So you have one exact sequence, which is the exact sequence of the D theorem. That goes to Hn pro étal. That goes to xRn. That goes to drRn. That goes to 0. But you have a second exact sequence, which so this one is actually a quotient of two complexes. It's a quotient of the complex, the de Rham complex, tensor B de Rham plus, sorry. So you have the complex, you have the de Rham complex, and then you have the degree R of the filtration of this de Rham complex. So this filtration is the tensor product of the two filtration. Here you have the Hodge filtration, and here you have the filtration of B de Rham plus. So it's a quotient. So, so you also have a long exact sequence of cohomology with the cohomology of the file R going to the de Rham cohomology, going to the cohomology of the quotient. Okay, so so you get maps like this. So this is Hn of file R goes to de Rham cohomology, B de Rham plus tensor Hn de Rham. And then you have the cohomology of the quotient, drRn. Sorry, it's not 0. And then it goes on. And here you have the Rn minus 1. And you have equality here. So you have a diagram like this with cohomology groups. And the conjecture is the following, that you can actually use this diagram here to describe this group. And so the conjecture CST is the following. So it's still a CN, Colmez-Niziol. So it tells you that this diagram is B-Cartesian. So it's equivalent to the fact that you can write down this sequence here, and it's equivalent to the fact that this sequence is exact. Short exact sequence, exact. So which means that you really describe this cohomology group in terms of de Rham data. Because I remind you, this is just Yodo-Kato, which is something that has to do with differential form, and this is a cohomology of some part of the de Rham complex. Okay, so that's the first part of the conjecture. So, yeah. And the second part of the conjecture, sorry, yeah. Second part of the conjecture is that you can actually recover the de Rham cohomology and the Yodo-Kato cohomology from the pro-étal cohomology in the following way. So if you look at Ohm commuting with Galois of this pro-étal cohomology, so Hn pro-étal, with value in B de Rham. So now you put 0 twist here. So maybe I should put YC QP. Then what you actually get is the de Rham cohomology. So the same degree of cohomology, but it's a dual and has a filtered K module. And now you can also recover, so that's what we claim, Sorry. So if you take the inductive limit of a finite extension of K, of the Hom commuting with GL of this Hn proetal with value in BST, then what you get is this Yodo-Kato cohomology, but the dual has a phi n GK module over CNR. So I should say that for algebraic varieties, all these statements are known now. Even if you don't assume your variety to be smooth and so on. But here, this is still a conjecture. I mean, we just stated it. And I should say that actually, Scholze does not believe in this conjecture. So you are free to try to find a counterexample to this conjecture. But on the other hand, I don't understand why he does not believe in it. So what can you prove about this conjecture? So what can we prove? So we can prove a number of things. So the first thing is that the first statement implies the second statement. So 1 implies 2. That's not so surprising because the first statement gives you a precise description of the proetal cohomology. And so from this description, it's not so complicated to actually compute these Homs, GK equivariants. And the second part is that conjecture is okay. So 1 is okay in the following cases. So if yk is proper, but this is not very interesting. Stein, so this is more interesting. So if it is an analytification of some algebraic variety. So more generally, if you take the complement of a small tube of some smooth subvariety of something which is proper, and also, yeah, some important case is that any product of the above. Okay, so basically, the theorem tells you that this conjecture is true in the two extreme cases of proper and Stein, which are exactly the two extreme possible cases. And it is also invariant, stable by products. And so, according to me, it gives a lot of confidence in the conjecture, but still, you have to convince Scholze. Okay, so one big ingredient is what we call geometrization of this proetal cohomology. Is geometrization. So what do we call by geometrization? it's the following theorem. So, which is also with Liesha. Which is we call the geometrization, is that this basic theorem, basic comparison theorem. So that's the one I just erased. Basic comparison can be sheafified over the category of perfectoid space over C. So what does it mean? It means, so if you take S, a perfectoid C algebra, so for example, you can take any of these CPs that I mentioned in the beginning. Then you can look at the functor that associate to S the cohomology of Y when you base change the scalar from C to S with value in QP of R. But you can also look at the functor that sends S be the RAM plus of S and BST of S. And so by the definition of the terms that appeared in the long exact sequence, you get a functor S goes to dr I of S, and S goes to xri of S. And the theorem tells you that the long exact sequence stays exact if you replace the objects that we had by these things where you extend scalar to S. Okay? And so you can summarize it by saying that you get a sequence of TVS. And so what is a TVS? So it's a functor, so it's a sheaf, sorry, on perf C with values in topological vector space over Q, so in QP topological vector spaces. So basic examples of TVS. Well, you have the one which we call QP underline, which sends any S to the continuous function on the connected component of the analytic space associated to S with value in QP. And there is a second one, which we call GA, which is very boring, it sends S to S. And a second one, which is a little less boring. So if you have a W, which is a topological vector space over QP, you can look at S goes to W of S, which is by definition where you extend the scalar to S, completed tensor product with W. Okay. And so there are two categories that you can build outside of QP and GA. Yeah, so this geometrization addresses the problem that I mentioned, that the cohomology depends on the field on which you compute it. Okay, so what it says is that you have some geometric object, which is this sheaf that controls everything. So BC is the smallest subcategory of this TVS, which is stable by extensions X and containing QP and GA. And we also define QBC to be the same thing, but you allow this W tensor GA. Okay, so I introduced this category under the name of finite dimensional Banach spaces with capital letters everywhere. So the specialists of finite dimensional vector spaces were quite unhappy with the terminology. But now everybody calls them Banach Colmez spaces, so I just call them BC, and that's why it's it. And so what happens is that, so there is no mention of these Fontaine rings of periods in the definition, but actually in this category are very much related to this ring of periods because of the theorem, following theorem, so of myself and Anschutz-Lebras. If you try to compute the Hom and the X1 TVS between this object, so if here you put QP and GA, and here you put QP, GA, and here you put again QP, GA, QP, GA. So you take the Hom from this one to this one. So here you get QP, here you get GA, here you get 0, here you get GA, and here you get 0, 0, here you get GA, and here you get GA. And so what are the extensions here? So this the class that generates the extension are the class, for this one is just the class that comes from QP B plus Chris, phi equal P, goes to GA, goes to 0. So that's the fundamental exact sequence. And the other one comes from a GA B Durham plus mod fields 2, goes to GA. So what it says is that all the extensions are built from Fontaine's period rings. And the xi are 0, or 0 for I bigger than 2. Okay. What is it? At 24. Okay, so I will skip these pages and I will turn to duality. So we want to explain this strange numbering that happened in my example. And so the conjecture is the following. So you suppose that y is of dimension d. Then the conjecture is that you should have an isomorphism. So the proétal cohomology of y with QP of j should be the Hom in this TVS category. of y with value in QP d plus 1 minus j. So, sorry, ROM of R gamma pro étal. Extension by QP of 1, and then shifted by dimension 2D. So that's the conjecture. And the theorem that we can prove is that this is okay if y is proper. But in that case, everything is finite dimensional, and then there is nothing to prove, basically. I mean, it's not true. It's a theorem of Zavialov and Lucas Mann. And it's also okay if y is fine. So that's what we proved with Viechar. And in fact, in that case, you have duality in the other direction. In both cases, you have duality in the other direction. So in both cases, both ways. So if we specialize this theorem to the unit ball, you get the following thing. So y is unit ball, open unit ball. So I remind you that we had this exact sequence of the boundary, mod O of the function, goes to H2 pro étal C of y QP of 1. And then there was a QP as a quotient. So this QP is just the ROM in category TVS of the H0 pro étal. But this one is just the X1 TVS of H1 pro étal, so ROM with value in QP of 1. So H1 pro étal of YC with value in QP of 1. With value, so the X1 by QP of 1. So the C that, so this one was a C vector space, and the C just comes from evaluating from this GA here. So when you evaluate your shifts on C, you get C here. Okay. So this is a C vector space, and the C appears as the X1 of GA by QP of 1. What? There is compact support here. Sorry. Yes. And so let me finish by a small remark. Is that remark? So this ghost circle that appear at the boundary of the unit ball, well, it behaves very much like a proper variety in the sense that the cohomology and cohomology with compact support is the same, but of dimension 1/2, which means of real dimension 1, if you want. And which means that, in fact, the 2D here is going to be 1. Okay? So I think my chairman is already up, and so maybe I should stop here, yes.
Thank you very much. And questions from the audience? Well, if there are no questions from the audience, let's thank Pierre again.